Hello. In this lecture, we'll go over Cormack-Jolly-Sieber open population models. I'll begin with some history and background, provide some information on the data type and multinomial model structure, go over the assumptions and violations, as well as extensions and implementation in Program Mark. The Cormack-Jolly-Sieber model was developed in the 1960s by Richard Cormack, who is now Emeritus Professor at the University of St Andrews, Scotland, George Jolly from the University of Aberdeen and University of Edinburgh, Scotland, and George Sieber from the University of Auckland, New Zealand. Cormack, 1964, estimated survival rates of northern fulmars. In that study, George Dennett captured and resighted fulmars at the breeding colony each year. From a commentary about the study, the fulmar may be the most long-lived of all birds, possibly achieving an age of 80 years or more. Scottish ornithologist George Dennett was photographed in 1951 holding a mature breeding fulmar which he had just ringed. The bird was captured again at the same site 30 years later, and George was again photographed with it. He had matured a bit, but the bird looked as young as ever. George Dennett died in 1995 at the age of 67. The fulmar, it is said, is still around this summer, still breeding and apparently untouched by the passing years, as of May 2007. There are similarities between capture-recapture and band recovery models, but there are also some important distinctions between these data types. Capture-recapture is done in a live context where individuals may be captured multiple times. Tagging of unmarked individuals and recaptures are at the same time and by the same people. The numbers of marked and unmarked animals are random. And there are equal numbers of tagging and recapture periods. From the band recovery of dead individuals, the bands of course are recovered only once. Banding in recovery are at different times and by different people, and the number of marked animals can be predetermined, and there can be more recovery than tagging periods. According to the CJS model, animals are tagged, released, and subsequently detected via recapture or resighting. The recaptures are conditional on releases of cohorts of individuals, and the CJS model is similar to the band recovery model in that the encounters can be organized into a triangular matrix. Because unmarked individuals are not a part of the likelihood, no estimation of abundance is possible. The model estimates two parameters, apparent survival and detection. Apparent survival means that we cannot distinguish between survival and emigration. Here is the basic sampling scenario for the CJS model with 4 capture occasions. At each capture occasion, individuals are captured and or sighted. Individuals are then released back into the population. There are 2 parameters, P and phi. P is the probability that a marked individual in the study population at sampling period I is captured or observed, and phi is apparent survival, or the probability that a marked individual in the study population at sampling period I survives until period I+1 and remains on the study area. Now let's review capture histories resulting from a sampling scenario with 3 capture occasions. The theta parameters represent the probability of observing individuals with different capture histories. So looking at theta 1, what is the probability of observing an encounter history with individuals released on time 1, are recaptured at time 2 and time 3? The individuals survive the interval between time 1 and time 2 with probability phi1, was recaptured at time 2 with probability p2, survived the interval between time 2 and time 3 with probability phi2, was recaptured at time 3 with probability p3. Now for theta 2, what is the probability of observing an encounter history with an individual released at time 1, was recaptured at time 2, and was not recaptured at time 3. The individual survived the interval between time 1 and time 2 with probability phi1, was recaptured at time 2 with probability p2, and now the 0 at time 3 can be explained by two processes. The individual survived the interval between time 2 and time 3 with probability phi2 and was not recaptured with probability 1 minus p3, or the animal did not survive the interval between time 2 and time 3 with probability 1 minus v2. On to theta 3. What is the probability of observing an encounter history with an individual released at time 1 that was not recaptured at time 2 and was recaptured at time 3? Because the animal was recaptured at time 3, we know the individual survived the interval between time 1 and time 2 with probability phi1, and this individual was not recaptured with probability 1 minus p2. The individual survived the interval between time 2 and time 3 with probability phi2 and was recaptured at time 3 with probability p3. Now we don't have to estimate the fourth theta for the encounter history for individuals that were never recaptured. However, I think it's useful to work our way through this encounter history. As above, the 0 in the second time occasion can be explained by two processes. The individual may not have survived the interval between time 1 and time 2 with probability 1 minus phi, or the animal survived the interval between time 1 and time 2 with probability phi1 and was not recaptured with probability 1 minus p2. Likewise, the final 0 for time 3 can be explained by two different processes. This last term in the brackets is the same as the term for theta 2, just that we used algebra to simplify the expression. This contains two processes that the animal either survived the interval and was not recaptured or did not survive the interval. We can visualize the model for the capture histories using a tree diagram. Let's say 55 individuals were released at time 1. Following these individuals through time, here are the individuals that were recaptured at time 2. Following these individuals through time, here are the individuals that were recaptured at all three time occasions. Here are the individuals not recaptured at time 3. Here are the individuals that were not captured at time 2. Following these individuals through time, here are the individuals that were subsequently recaptured at time 3. And here are the group of individuals that were never recaptured through the study. Then we can multiply the probability of observing each capture history by the number of individuals released in cohort 1 to estimate the expected numbers for each capture history. From this, we can see the probability of being encountered at a sampling occasion is governed by two parameters, phi and p. Here are the capture histories for the first cohort released at time 1, represented by R1. We will use the notation chi1 to indicate capture history for individuals never recaptured. This slide shows the multinomial likelihood based on encounter histories for the first cohort and reads the likelihood of parameters phi and p given the data for cohort 1 and the vector of capture histories. And here are the probabilistic arguments for the capture histories built up into a multiplicative likelihood. Here is the set of capture histories for the second cohort released at time 2. Again, the individuals never recaptured are represented by chi2. Now we can build up the multinomial likelihood function for both cohorts. Here's the likelihood for cohort 1, likelihood for cohort 2, and the full likelihood is the product of the likelihoods for each cohort. The capture histories can be summarized as a triangular MIJ array. The x-axis represents the number of individuals captured and released for each cohort, 1 through 6. The x-axis is represented by the number of capture occasions, 2 through 7. And the values in the MIJ array are the number of marked individuals released in cohort I that were first recaptured in occasion J. The cohorts for the number of marked animals released at each occasion can be considered the number of multinomial trials. The observed values in the MIJ array for the number of marked individuals released that were first recaptured in each occasion can be considered the multinomial outcomes or random variables. So going back to our example with 6 cohorts and 6 capture occasions, the cohorts are the multinomial trials, and the values in the MIJ array are the outcomes or the random variables. Then we can use probabilistic arguments for the parameters phi and p to model the MIJ outcomes. And here is the alternate likelihood for the MIJ array. So the likelihood is equivalent to the way we did this for the encounter histories. And here is the likelihood for the first cohort that reads the likelihood of the parameters phi and p given the data for cohort 1 and the MIJ outcomes for cohort 1. Here are the probabilistic arguments for the MIJ outcomes built up into a multiplicative likelihood. Then we can build up the full likelihood as a product of the likelihoods for the different cohorts. Here are the assumptions of the CJS model in terms of study design and field procedure. Marked or tagged individuals are representative of the population. The number of individuals released for each occasion is known, and the releases are instantaneous or occur over a short time period. There is no tag loss or misidentification, and the survival or detection probabilities are homogeneous unless accounted for with covariates. And all emigration is permanent. In terms of stochastic effects, the fate of each individual and cohort is considered to be independent. We may be able to relax the assumption of homogeneous survival or detection probabilities by including a trap response on survival or the capture rates. We can also soak up heterogeneity in the parameters using 2 groups for transients or residents, age models, or covariates, including time-specific or static individual covariates. I'd like to conclude with a brief discussion of parameter identifiability in the CJS model. We can rewrite the probabilistic structure for the models using beta 3 to denote the last phi and p that can only be estimated as the product. And Mark does this for you in the model. And in this case, the model has time-specific parameters for p and phi. That is, there are time-specific estimates of phi for each interval and p for each time occasion. But if we were to constrain p or phi to be constant across the time occasions, then we would be able to estimate the last p and phi for this model. Graphically, we can see the problem of estimating the last phi and p in a time-specific model. Basically, we need 2 occasions to estimate apparent survival and detection, so we are unable to estimate the parameter for cohort 3 in this model.